Thanks so much for joining me on this panel, which is supposed to be a bit a time capsule looking to the back, to the current, and to the future. So maybe just starting a bit from today, basically, maybe Daria, you want to start. What do you find, even in a fast-moving company and with fast-moving engineering processes that you have implemented because you needed to scrape with a small team to make possible what is possible, what do you find the most frustrating and maybe challenging with the engineering process of today?
All right, that's a very good question. What I personally find the most frustrating is the changing requirements from customers and managing these requirements. So yeah, as soon as you're finished your beautiful electrical design to interface the camera, for example, and then customer just decided to change SPI interface to LVDS and decides to tell you just before you prepare the manufacturing files, that's something which is I find frustrating. So yeah, that's requirements that are changed fast from the customer perspective.
So both in the good and the bad parts, we have the humans back in the loop. And then Livingston, with your experience, I'm curious to hear, like, when you compare how engineers worked 10 years ago and then how engineers work today, what do you think have been the major breakthroughs of the last decade of how engineering has evolved in these last 10 years?
I think the thing that I've noticed the most is the acceleration of use of computing for everything from modeling, computational fluid dynamics to figure out what can we really do in the air, what can we expect, how will the engine actually perform. So the CFD models have really improved, but I've seen some of the younger engineers take very complex models that take hours to run and find shortcuts that give you good answers quickly so that you are tracking in the right direction. And the other thing is their ability to communicate quickly over by electronic means, no matter what they are. And so I take that cue from the younger engineers who accelerate communication with each other collaboratively, informally, and find ways to take sometimes older, clunkier tools and make them faster.
So heritage, yes, but with a new spin to it. And Dan, what do you think? What excites you about how you have assembled your engineering team and way of working that you think that others could learn from, that you would like to give to others, even if they're not developing fusion reactors, but other things?
Good question. So I think there's probably two different things. I think it's one is looking across industries for good engineers. Like, so what we're doing is a kind of, we like to say it's an aerospace project surrounded by a bunch of infrastructure. So we're pulling from people from the fission industry because they're more comfortable with the infrastructure side of things. There's a little bit of radiation going on, so they have good practices for handling that. But then we're building a really high performance cutting edge engineering system, and aerospace is quite often the best place to get those types of people because they're also at the cutting edge. And secondly, I think it's how we've empowered our people to make decisions. We've basically tried to make it very clear that people at system ownership, we call them system responsible officers, those people at those level, if the decision is just contained to your system and you can still meet your requirements and don't blow your budget, that you can make the decision yourself. You don't have to keep on escalating it up. It's only once it starts interfacing with other things, you got to talk to the right people then. Or if you really do think it's kind of a strategic level decision, we've got a thing that sounds far too formal, the technology review board that we use to help guide the people through making the decision process.
Nice. How about you, Livingston? When you think about how, I mean, you're the early part of your of Radian and assembling the team and bringing those things together. But what have you learned already on that that differs from other ways of how you've assembled teams in the past that others could learn from?
Yeah, because I've had experience, you know, in Air Force, Boeing, et cetera, they were very structured, almost top-down enterprises, and so you bought engineers by the slice, so to speak. Well, I think this project needs this many electrical engineers, this many mechanical, and this many aeronautical, and you can sprinkle some aerospace guys in there for fun, you know. And so we would do that structured, this is what the project needs, and that's what we would go hire, and it might not actually be what the project needed because it was, you know, the chief engineer's view of what the project needed. The difference is now I'm looking for good athletes. I'm not necessarily looking for a second baseman or a shortstop. I'm looking for somebody who is good on their feet thinking and has technical skills in one of the domains of interest for us. So that agility to not necessarily be too specific in one area. I'd love to have those skills, but I need the agility more so than I do that precise skill, because everybody ends up doing everything or more. So if I know what you need, my job will be better done if I am providing the information that actually is valuable to you. So that type of collaborative thinking is what I'm looking for as I hire engineers, you know.
And that's what resonates with Daria, with your talk, right? When you were saying that generalists sometimes help you more. Daria, maybe when you look at the near-term future of things that are possible to do now or just are becoming possible to do now, what excites you the most of what's just about to come in your area of work?
Right. What's also about my personal pain points, as I'm participating in quite many proposals preparation, there are certain automatic tools which help you a lot to speed up the process, but that's more on the project and management side. In terms of engineering and systems engineering, there are also quite many tools to collaboratively work together and make decisions together. Plus, there are cool tools that help to effectively work with remote teams. So that helps us a lot to attract talent that is not present locally in Germany or in Berlin, but still wants to help us build in our projects and services. And the third one is the communication related. So there are certain tools that help us to improve the knowledge transfer between different teams and within teams.
And diving in, and I think you said on stage before that you're using Miro boards quite a lot and that you like the way of being able to whiteboard. That's super interesting because over the course of the last 2 days, I had many people telling me I can do everything online minus whiteboarding. And I know that many of them have tried Miro. So what do you think have you found out as a process for your team of making that tool work? Does whiteboarding work the same way digitally as it does in presence for you, or are you doing it in a different way so you can make it work?
I think it's the matter of preparing that one. So if you have the defined structure where you know step by step what you can add, where you can write, and how to connect things, it helps a lot. If you have just an empty whiteboard, there's certain brainstorming possible, but it helps a lot to add this structure. So that helps us a lot with mission definition. We do have quite specific questions which we figure out help us the most to optimize the mission preparation. And then you jump into every step of concept of operations that your customers are actually understanding how it's going to be once the satellite is going to be over there, and to rethink all the mission parameters that they should have thought way earlier while applying for the mission. So I think it's a lot about the preparation and the structure in the end, but it gives you a lot of freedom in working together still.
And from technologies now already looking a bit into the closer future, present and closer future, we heard about ways how AI can and will shape what we've been doing. and how optimization can and will shape, then what kind of role do these two things already play in your team today, and what kind of role will they play, I don't know, the moment that your reactor is up and you're doing the second, third, fourth?
Yeah, so AI is kind of a loaded term, so I'll try to define one aspect of it. So the massive machine learning types of things, we're not really doing that yet, because quite simply we haven't quite figured out how to. We're starting to explore partnerships with places that could help us do that. But just in a more broader sense, like certain modern optimization techniques, our collaborators at MIT recently published a paper where I think they're able to 10x the speed of their super ridiculously complicated fusion turbulence simulations, because they were able to use the AI to adjust which parameters the simulation was set up with, to such that it converged much more quickly. So it's using it like that. And then looking forward to when we actually have fusion reactors going. I'm kind of a skeptic and an optimist at both times with AI, and I'm sure that we'll have it involved in ways like they're saying they're doing at SpaceX. We're doing these things locally, measuring, taking the data and using it to process it and understanding it. But I think there'll always be a role for people who deeply understand the technology from a fundamental physics level that need to push it forward as well.
How do you deal with this uncertainty that black box models are trying to like predict things that you as an engineer might not even understand? Livingston, for you, is AI this buzzword, and because the principles below it, without fully understanding, like you said, you need to understand the depth of it, will not be helpful? Or do you just need good judgment to know if the outputs can or could make sense?
I think for the problems that I see, that I face, AI will be helpful in the future, but we don't have enough understanding of the physics problem to actually feed it well. Specifically, the thing that concerns me the most is our computational fluid dynamics models, our CFD models. We do not have good models that run from subsonic, which is our landing condition, transonic, which is our takeoff condition, and shortly after takeoff, supersonic, and then hypersonic. Each model runs well in one domain only, and they tend to be tuned toward vehicles that typically fly in those domains. So hypersonic vehicles are often propulsive vehicles. They're typically small, they have thin wings, and so if I look at a hypersonics model, it will come from that regime, from folks that are solving that problem. I've got a big bird that I'm pushing through the air really, really fast. And so the hypersonics models don't kind of look like me. So I'm trying to figure out, how do I leverage this patchwork of aerodynamic analysis models together to come up with a true flight model? And I have to do something in a wind tunnel to anchor it, otherwise it's just a computer talking to itself. You know, it says, I think this cell is going to do this next, hand it off, and calculate what comes next. And there's no basis for it. I think with AI, we would be able to, you know, imbue some of the knowledge of the people who are making judgments based upon what they've seen into that computing model, and actually start to stitch together something that is more coherent, that would provide us with better optimization of both flight paths and vehicle structural aeroform designs. So I think it's out there, but I can't grasp it quite yet. I know what I'd love for it to do for me.
And when we're talking about, like, for example, in the talk from Johannes before, we saw the power of optimizing between design choices. And Daria, when you're saying, right, like you have these customers and they come up and they say, well, in principle I want this, or in principle I want that, and you map that to the things that you've done before, and you're basically doing a lot of that optimization with your knowledge and your experience. How far are we from going one step further and having that kind of optimization being assisted? Or do you think at this level, gut feeling is gonna be the thing outrunning models for quite a while?
So here I would agree, there's not enough, I think, data to feed those models for them to get solid results. Where I see the certain opportunities are in commissioning and operations. So once we're talking about constellations of of many, many satellites, there we will finally get lots of data on how satellites are feeling, how they're behaving, what's going wrong. And in that regard, it would be possible to automate certain processes. We had a very cool feasibility study on the topic on scheduling. So basically, scheduling between different payloads, trying to optimize the scientific value. If different payloads require different power, different radio access, different types of attitudes, we were evaluating if we can use AI tools or certain tools to optimize those. Actually, we figured out that yes, at the moment that would not give us sufficient results with also capacities, computation capacities that are available in the satellites. Yeah, still was quite a cool study, but I definitely see the opportunities in constellation management.
In the coffee break, I went downstairs to the wall, so thank you very much to everyone who actually put Post-its up on the wall with the same question that we have up here. And I'm just picking 3 things that stood out a bit to me and packaging them a bit as questions. So one I found interesting when it came to what needs to change for these next 10 years was we should include more the social science. And I'm very curious, Dan, you're saying, let's look at different kinds of engineering to bring a broader variety. Are we looking too short? Should we actually look even a step further? And if people maybe have the right tools, then the right skill sets come from very different places? Or is engineering bound to be a domain which should be left to the engineers?
Well, I'm definitely not going to have a social scientist do the calculations for my engineering project, but engineering is inherently an interaction of technology with society, and at the very least, the social scientists and everybody that has a role and participates in it should generally have a voice in what we're building for them.
And one other part which was mentioned downstairs, Livingston, it said 3D printing and 3D design is still going to change the next 10 years.
Oh, yeah.
I have heard that for the last 10 years, and the ultimate idea that we were given that we would all have our 3D printers at home and have all the spare parts for every aspect all the time available has unfortunately not happened.
No.
However, there are people building entire rocket engines and so on from scratch. Where do you see generative design, where do you see 3D printing going in the next 10 years with what we now know what's possible and what we now think could be possible?
One of the limitations that I see on 3D printing is scale. There was a technology we were looking at to build our full-scale engines because a powder bed doesn't do it. You've got a volume that's controlled, and you've got sintering that goes on within that powder bed, and you end up with spalling and other defects that can occur as a result of that. And we were looking at cold spray additive manufacturing. So I think that there's still room for 3D printing or additive manufacturing to grow, because I don't think we've explored the entire volume of what's possible yet. Now, we do have areas where we're getting really good. We're getting sufficient performance part over part that meets aviation standards, which means that I'm going to put this part in a commercial airplane and fly it and trust that airplane with this 3D printed part will not fail while we're in it for the life of that airplane. And so we're getting to that level of quality now. Processes that are new do not take over overnight, especially when they have to meet requirements for human safety. I can make as many face plates and doorknobs as I want with 3D printing, And the worst thing that will happen is that if I drop it, it'll crack or break or, you know, something. But it's not going to, you know, it's not going to cause an impact on a bunch of lives. So when you're talking rocket systems, aircraft systems, you have to think, that social science piece, what you're doing from the value of the humans that you're carrying. You have to believe that as a sacred trust between you as the builder of this device and that person who's getting on the plane to go see a family member that you've never met. So you have to believe that sacred trust carries through. So when you look at 3D printing and other additive manufacturing technologies, once you get into that domain, the quality has to be every bit as good as anything we can produce using any other technology. Now, the power of that is it allows us to replicate those parts with high accuracy, high repeatability, and at lower cost. So now the efficiency of that product goes up. So once you get over that hurdle of ensuring that you've got the quality of the part, you now get to take the advantage of the backside of it, which says it can make a lot. Limitation right now, composites. You know, composites are generally laid up, you know, layer by layer like fabric and you know, infused with a resin or some other system and squeezed and heated and, you know, pressed in an autoclave and then come out and they trim it. Ooh, hard to 3D print that. There are areas where thermoplastics can be 3D printed. But, you know, if your design requires a thermoplastic that can be 3D printed, you win. I'm not even sure what materials I'm going to be able to use that I could turn into a 3D printer for, because I may need a bismuth or, you know, a material that can take both cryogenic and high temperatures. And I'm struggling with that battle right now. And those are all different systems that none of them right now can be 3D printed. But I hold out hope. I hold out hope.
But it's interesting to what you just mentioned. It resonates with what Alexander just said in his talk, right? The level of safety that you have to guarantee today is not what probably in your early career you had to guarantee, right? So we have to innovate now to a level immediately that is at our current safety and understanding and level and cannot take the risks we did before.
Think about the fact that rockets take off near water so that, one, their booster parts can fall into the water, and if something goes wrong, we can blow the rocket up and its parts will fall into water. So we're already predicting some degree of failure based upon our history of these things are hard to build and often go awry. So when you think about the fact that we're not that confident that we can take a rocket off from inland and fly over uninvolved populations without risking them, it means that we're not quite there yet. You know, we hope to get there, but we're not quite there yet.
And that maybe again towards the point of looking a bit beyond the boundaries of the technology. A last point that I saw on the wall downstairs, Daria, maybe the ask was, what needs to change in the next 10 years? And the answer was simply being more diverse. How do you see that? Is that an opportunity that we're still currently missing and where we could do far more about?
I think so, yes. If you look at the audience, I think it's mostly male-dominated. I think we need more women, first of all. I think diversity is beautiful, brings new perspectives and new inputs. I love working in the team where all age is represented, so there's a solid knowledge transfer and energy transfer back. There's a balance of speed and knowledge as well. So I think it's still a lot to do, but we are on the right path, I think.
I love that cycle that you just described, like the knowledge transfer and energy transfer in the other direction. I think that's something to definitely look out for and maybe to design for, like when we design our teams. Looking now from the near future into the very far future, so I just put 10 years there, but I know that all of you are like working on also far longer time scales, so let's extend that a bit. So what kind of trends then do you see that are long-term trends in engineering and long-term trends in technology that will completely redefine what we're able to build as humans in the longer term?
Yeah, so one part of this goes back to your earlier question on AI, just the power of computation, how it's increasing just absolutely exponentially. Our ability to do very complex simulations just in the short period of time that I've been working on it. I can't imagine it was like back in the day when you were punching cards, little hole punch.
So you really do know my history.
Oh yeah, I looked it up. Let's see. Yeah, that just the power of computation to be able to do high fidelity simulations and to actually do, like, have a very high confidence of how it's going to perform before you build it. But it's always still critical to actually go forward and build it and make sure to get the real life analog tests going. And that then further coupled with things like advances in material science and how material science is really the fundamental thing that limits what we're actually able to instantiate in the world. A couple of computation, I'm just super excited about what things we'll have to build with in the future.
Yeah. Let me amplify that point, because right now when I do a CFD model, I end up with in my mind, it's a big cube of numbers. And in that cube of numbers, if I fly the vehicle at this attitude, this altitude, and it's in this velocity, I know what the performance of the aircraft is at that point. At that point. Now I have to figure out what happens next. What if that's not the path I chose? So the computational work, just to figure out our flight path, or what the predicted flight behavior of the system is, takes up enormous amount of compute time. So probably not nearly as much as your stuff, but I'll say, how long do we want to wait for to get an answer or a series of answers? And we'll let the machines run over the night, over the weekends, et cetera, and we'll get this volume of numbers that we have to now do something with. And that's for these different points of the vehicle's performance. So when we're able to do quantum computing, which will allow us to take the weekends of the computer's time and accelerate that to maybe a day, maybe an hour, maybe a few minutes, all of a sudden the amount of computational power will accelerate what we can do enormously. So I'm really looking forward to that, because it means problems that we think we know how to solve, we can just have the computer crunch it and actually get answers in a reasonable amount of time. So I'm really looking forward to that.
But isn't it interesting how that mega trend goes against the trend that we're seeing today for companies becoming more agile? I have the feeling that we heard a lot, like, remember Skylar's talk or other talks, it was always like, sometimes screw the simulations, let's get something real in real conditions as fast as possible, because that's anyways going to tell us more. But the mega trend tells us we're going to be able to simulate so much more, which will prevent us from needing to build so many things. How come that the short-term trend is into less simulation, more trying, and the long-term trend is maybe again into more simulation before you try?
Let me take a little bit of argument with that. We built a rocket engine that we thought was going to be the rocket engine for us, and we put it on the stand. It's a 200,000-pound thrust class LOX Jet A engine, and we fired it in a few years. Everybody said, "You did what?" And so we built hardware, but that informed what we really could do with that hardware. So building it was good, but the analysis of how the system performs in total still needed to be done computationally, because I can test it in this environment. I get a sea level test. I don't get an altitude test of this system unless I fly it. So I can put it on a demonstrator vehicle and fly it. So I'll have that test of that system. But the number of variable conditions that I'm going to face, I can test a few, but I can't test them all. But I have to have sufficient knowledge about all of them before I know that I've got a safe flight envelope. I have to know what happens at the edges. And I can think back to when I went through test pilot school, and we were flying T-38s, and we're at the edge of the specific excess energy curve. And I've looked at all the curves, I understand it mentally, and we're flying and the airplane starts to chatter. and I'm feeling the chatter, and I stop pulling on the stick. And the pilot, the aircraft commander, says, we're not there yet. And I'm looking at the G meter, and I'm going, I know we're not there yet, but the plane doesn't feel good. And he takes over the aircraft and says, I have control, and pulls it back. The aircraft is chattering so much, I'm wondering if I'm going to lose fillings in my teeth. And he said, that's what it feels like at the edge of the curve. He had that experience flying. The calculations said that's where it is, but you also needed to connect that to what the system really felt, but we didn't have accelerometers in the system that says, this is the chatter you're gonna feel. The pilot had that, and that's a seat of the pants kind of thing. So you will need to do flight tests, experiments, et cetera, but you have to have the computational work to know where the edges are, you know, and where the optimization trails are, so that you don't pop out of them and spin out.
I agree with him a lot, and I just want to add that it really, both of them work hand in hand, and you need both of them. And I think it really, which one you choose to do when really depends on what resources and capabilities you have, and then you make a wise choice based off of that.
Yeah.
And if engineering is gone already very different than 10 years ago, but textbooks are taught, or classes are taught with textbooks from 10 years ago, from professors who maybe worked 30 years ago, to prepare us from what's coming 20 years from now. Daria, what would you tell to an engineer who starts engineering career today, what to learn, what to do besides the normal classes that prepares them a bit for what's coming, if there's even anything like preparing for the future?
The YouTube videos. There's so much stuff over there. Like, I personally love tearing down videos. But no, there's so much knowledge, and there's so much like online classes at the moment which share like pretty much everything from Aerospace to anything you can imagine. But if we're talking about the next and the preparation for the next 10, 20 years, I think fundamental background, fundamental basis of understanding how things work is something which is very important, and which on top of that you can really build pretty much any knowledge in any domain.
Did she say it's good to know how things work? That was the title of my presentation.
As if you had foreseen it, Livingston. So when you're imagining the engineering team's office of the future, right? So people walk into CFS 20 years from now. What does it look and feel like?
Well, first of all, it's powered by fusion energy. And then second of all, I think it's really interesting what this pandemic has shown, how effective teams can be working remotely. Certainly is learning curve for many people to get over that, but that really excites me, and the ability to have a very distributed team being able to work together and contribute together in new ways. I think you can really actually build a stronger team doing that. But then that doesn't leave the fact that we have to build hardware, and there has to be people in centralized locations doing that too. Like if we're just doing paper studies all the time, I quit. But you have to. I think it's exciting. It's probably going to be a merger of those two worlds, and I look forward to it.
That makes sense. I want to open it up for questions from the audience at this point.
I have a question about IP rights. When you work in different places, different people working remotely, what is an idea about keeping IP rights and security of the information protected? It's easier in one building, but if you work everywhere, it's a higher risk. Huh?
Well, it's not only, I have to deal with our IP, so I'll start on this. It's not only a high risk because people are spread out, it's just a high risk because you're using computers, and your computer security is only as good as your least secure person that has access to the network. And that is frightening from that standpoint. And so what it points to is something like the talk this morning was talking about, is like the most successful businesses might not be the ones that very securely and tightly hold their IP to their chest. It's the ones that are able to innovate faster than anyone else and just basically get out and run ahead.
Yeah. I think that cloud computing systems and other systems are becoming more secure. We're thinking about this problem more deeply than we have historically. And because the work I do is all ITAR controlled, and there's a defense and intelligence community aspect to the value proposition of what we do, we really try to manage what we can share in what level of detail. And we're putting in place what's called the FedRAMP, environment, so that everything we're doing is encrypted. It lives in a secure location, and so it doesn't get disseminated easily. But to your point, the security is only as good as the least secure person. So if someone is careless or nefarious with your data, they can let a lot of it out, and therefore your IP goes with it. The challenge is it's not just IP, but it could be classification information that gets out with it. So I'm watching the computing environment mature very, very rapidly around this area, but it still requires humans to implement properly. And we're probably more leaky than the computers are.
But Dan, what I understand from your answer is also, if you can run fast enough,
yeah,
even if you handed someone all of the information, ideally, they're never going to be able to execute on it on a time scale that is relevant, because you're always one step ahead. Is that what you meant?
Yeah, I suppose it's a strategy and a bit of a hope, and it's borne out by some companies' techniques, and hopefully we'll be able to make it successful as well.
Yeah, actually, it's an interesting entry to what I wanted to open up a little bit on. A few times in the last 2 days, there has been a talk about open hardware or things that we should share more to approximate the software ecosystem a bit better and to accelerate. So I was wondering what the thoughts were on that in terms of, like, yeah, you say you need to be faster than everybody else because the IP is not protectable anyway in practice. But doesn't that also, I mean, open up the opportunity to share everything anyway? And would that be a great accelerator in, like, the acceleration in software might be just the fact that there's open source. How about open hardware?
Yeah, so maybe not necessarily open hardware for us, but we do have a whole entire arm of our organization that's called Open Innovation, and we do have, I don't know if it's a value or some other HRE term, that we have a default to openness, and where that we published our scientific basis on what we're doing. No other private fusion company has done that. In addition, we're giving detail, kind of broad strokes engineering details of what we're doing in hope that other people out there will pick it up and start working on some of the problems because they think they're interesting, they think they're worthwhile to work on. And just because they're working on a subset of the problems doesn't mean that they steal our whole entire value chain. It actually ends up being, we hope, additive to it. And of course, this is an experiment we're performing right now in live time.
I can speak a little bit for small satellite community. There are a couple of open projects which host hardware designs for structures, for onboard computers, for electrical power systems. And they're open, everybody can download them, as well as also certain operating systems for small sats. These are communities that are quite small. They've reached, I think, their limit in terms of like number of people interested. It's still a little hard to maintain. So it's more on the amateur level where there are certain additions to design. Like design iterations are much harder to maintain. Not so many people have enough budget to actually test what is maintained by community. But yeah, in small satellites, they exist. I think they did launch maybe like one or couple of satellites. Most of them like are university level communities. So there is one. No, there are a couple. Not super successful, unfortunately.
So you discussed additive manufacturing, you discussed AI, and it seemed a lot like not yet. Are there technologies or other directions that people are heading where you think it might be a dead end, or something that people should be not distracted by when pursuing the things that really, really matter?
I can start with one. So at least from a software tool perspective, I think people who are actively trying to make engineers obsolete in the sense of thinking things through, I think it's a dead end. I do feel that AI and other things will be one more tool in the tool chain of engineers. I think anyone who believes that you'll just have an interface you talk to without engineering background and you say, I want this, and then at the end of it, all the engineering has been done by a system that can do this, I think we're at least not our lifetime close to that. And I think people who are trying to sell that today, that they can, are using lots of smoke and mirrors. So in my view, it's more important to find the things that can give value today and tomorrow from the technologies that we see and give them into the tool chain instead of trying to jump all those steps ahead.
I wouldn't say not yet, because I think additive manufacturing has a good place now. I think there is a lot of excellent work that is being done, and you can buy products or build products with additive manufacturing technologies. I think that its depth into, say, the aerospace community is not there yet, because you're going to have to jump through bigger or narrower hoops to get all the way there. So I think that the work that's going on today is actually foundational to the work that will happen tomorrow, and I think it will help accelerate the work that happens tomorrow, because more people will be accessing the technology, pushing the technology, and once that broader population gets access to it, I think its growth grows much more rapidly. So for my particular application, not quite yet. Subsystems within mine, turbo machinery, et cetera, housing structures, there's lots of stuff that it's absolutely ready for today. So, and I think AI is kind of the same way. It all depends on where we are on that curve. And we're not quite there yet for my application, but I do see it.
So one that has a little bit of overlap with what I do and what a lot of you do, fusion rockets. If anyone is trying to sell you a fusion rocket, just turn around, walk away. Until we get it working on ground, then it might come a couple decades later.
Yeah, yeah. And really, really, really big. Yeah. Really,
big.
Really big. Somebody there?
Last question over here.
Individually, what's the tip that you give to the people that will be in your spot in 10 years? So for the students and the newcomers, what's a tip that you found in your own experience that you want to give to those people?
As the elder statesman of the entire group, you know, so when, what are we, iteration 22? It'll be iteration 32 at that point. So 10 years down the road, it'll probably still be me here. But one thing I do encourage is the students that are out there, those that are still on the growth path of their careers, learn what you can from whomever you can and from whichever source you can. The curiosity that you have today will be rewarded, I believe, with a rich future of options for you to do more than you might think you can do in one lifetime. I think I'm a living example of that. I encourage the youth to talk to senior folks, because we like youth talking to us. Somebody still needs to talk to us. But I think there's a lot of learning that we can pass on, experience that doesn't come just from a classroom or a book or even a YouTube video. I think that hearing and conversing with folks that have done different things is valuable for those students. And you are always a student. You are a student when you graduate and you get your degree. You're a student when you enter your first job assignment. You're a student when you leave that one and go to the next one. You are always, always, always a student. So never turn off the spigot of information coming towards you. Always take advantage of it and leverage it and relish it.
Yeah, I really agree with everything. Or maybe to add on top, to try as many things as possible. Yeah, to be open to try like changing different fields, different sectors, and to try as many things, to try to break as many things, to try to build as many things. Yes.
Yeah, when you ask someone why they're doing something there, and they say because that's the way we've always done that, that's when you know you should probably do it differently, and trust what you're thinking of how you should do it.
And I think that's a great part to the last question that I have for the three of you. And if the engineering fairy comes and grants you a single wish for what you can get in engineering in 10 years, what are you going to ask that fairy?
Unobtainium.
Oh, that's a good one. I like that.
I'll share it with you.
Okay. Wow. So what are you going to ask?
After that answer, I don't know. I have a less creative answer, but like to leave all the work related to documentation behind and focus on creative and beautiful engineering tasks to solve. Yes.
You know, I think that because he's going to share the unobtainium, so I don't have to ask the engineering fairy for that because he's going to give me some of his. But I think what I really wish for is a curious and intelligent future workforce. I look at some of the younger people entering the workforce, and I say, I really wasn't that smart at their age. And I just want more of that. And I also see collaboration between these younger folks that I didn't see before either. And so I'm looking for that interactive, collaborative, curious, energetic workforce of the future, because you are going to create, they are going to create the stuff of the future for the rest of us. And I think it'll just be marvelous. So that's what I'd like.
That's beautiful. And since we're here to engineer the impossible, maybe we don't need a fairy to get all the things that you just wished for. Thank you very much for being the participants on this panel.